In last episode, we did a review of groundbreaking papers that have shaped our understanding of Albert Einstein's revolutionary theory of general relativity and its profound implications for the cosmos. In this episode, we will examine the most significant papers discussing quantum mechanics and its implications. In 1900, Max Planck proposed a groundbreaking hypothesis to solve the black body radiation problem. He suggested that energy is not emitted or absorbed continuously, but rather in discrete packets or quanta. This was a radical departure from classical physics, which viewed energy as a continuous variable. Planck introduced the concept of the Planck constant, h, now a fundamental constant in physics, showing that the energy, E, of these quanta is proportional to the frequency, ni, of radiation, with E equals h ni. Planck's quantum hypothesis is now viewed as the birth of quantum physics. Albert Einstein's explanation of the photoelectric effect in 1905 provided crucial evidence for the quantum nature of light. When light shines on a metal surface, it can eject electrons. Classical wave theories of light couldn't explain why there is a threshold frequency below which no electrons are ejected, regardless of the light's intensity. Einstein proposed that light is composed of particles, photons, with energies quantized according to E equals h ni. The photoelectric effect demonstrated that an electron can be ejected only if it absorbs a photon with enough energy, thereby confirming the quantum nature of light and further supporting Planck's hypothesis. In 1913, Niels Bohr developed a model for the hydrogen atom that incorporated quantum theory while also respecting the structure of the Rutherford model. Bohr postulated that electrons orbit the nucleus in certain allowed paths or orbits without emitting radiation. Transitions between these orbits result in the emission or absorption of energy in discrete quanta, photons, which could account for the observed spectral lines of hydrogen. Bohr's model introduced quantization of angular momentum and provided an explanation for the stability of atoms. Erwin Schrödinger, in 1926, formulated the wave equation that describes how the quantum state of a physical system changes over time. The Schrödinger equation is a fundamental equation of non-relativistic quantum mechanics that treats particles as wave-like entities where the waveform represents a probability amplitude. The equation allows for the calculation of the probability distribution of a particle's position and momentum, leading to an understanding of atomic and molecular structure that is central to quantum theory. Werner Heisenberg introduced the uncertainty principle in 1927, which is a cornerstone of quantum mechanics. It states that certain pairs of physical properties, like position and momentum, cannot be simultaneously measured with infinite precision. The more precisely one property is measured, the less precisely the other can be known. This is not due to instrument imperfections, but rather a fundamental property of nature. The uncertainty principle challenges classical concepts of determinism and revolutionized the philosophical underpinnings of physics. The EPR paradox was formulated by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. It challenged the completeness of quantum mechanics by describing a thought experiment where two particles are entangled in such a way that the measurement of a property, e.g. spin direction, of one particle appears to instantaneously determine the property of the other, no matter the distance separating them. This seemed to violate the principle of local realism, which states that an object is influenced directly only by its immediate surroundings. The EPR paper aimed to show that quantum mechanics might be incomplete as it fails to account for these hidden variables. John Bell's theorem, presented in 1964, is a pivotal result in quantum physics that addresses the question of whether particle properties are determined by hidden variables as suggested by the EPR paradox. Bell's theorem shows that no local theory of hidden variables can reproduce all the predictions of quantum mechanics. His inequalities are designed to test the difference between quantum mechanics and local hidden variable theories. Experimental tests of Bell's inequalities have generally supported the quantum predictions and the existence of entanglement, thus reinforcing the standard interpretation of quantum mechanics over local realism. String theory emerges when attempting to combine the principles of quantum mechanics and general relativity. In 1995, Edward Witten published an article titled String Theory Dynamics in Various Dimensions, in which he argues that reality is 11-dimensional. Throughout the article, Witten establishes a unification between different string theories, later called the M-string theory. An interpretation of the string theory suggests that our universe might not be the only one. Instead, there could be many other universes existing alongside ours in a larger multiverse. Each of these universes might have its own unique set of laws, constants, and properties that govern how things work within them. This concept of multiple universes with varying characteristics is a fundamental aspect of string theory and its implications for our understanding of reality. The idea of dimensions beyond our perceivable reality raises intriguing questions if we, as humans, are limited to experiencing only 4 spatiotemporal dimensions. Moreover, could these extra dimensions play a role in shaping the fundamental principles of biology and the evolution of life itself? In the next chapter, we will examine the most significant papers discussing quantum biology and its implications.